Our final example is going to be of an initial value problem which does not have any solution at all. And in this case, actually, it should be not so difficult to see because, so if I have an equation like this, an initial condition y of 0 equal to minus 1, then clearly at the initial point, if I try to compute the derivative, I'll need to calculate so at the initial point. And the initial point is x is equal to 0, y is equal to minus 1. We have y prime equal to 0 plus minus 1 to the power 1/2. And the right-hand side is undefined. And so because y prime is undefined, then the equation actually does not make sense at the initial point. And so therefore, we can't have any solution. Okay, so we will finish this with a little bit of theory. So what kind of questions one would want to ask when you see an initial value problem? You, of course, at the end of the day, you want to solve it. But even before you solve it, you might be interested in the following two aspects. Number one, we hope that we're not in this situation when the problem has no solution, because if somehow in advance I know that the problem doesn't have a solution, then it makes no sense to solve it. Or if I'm not sure whether or not it has a solution, I have to somehow conduct an investigation of whether or not the solution, it is worth pursuing the solution at all. The second thing that you might be interested in, if you're solving a realistic, let's say, problem that comes from physics or engineering, then typically you would expect, if you, in engineering, if you'd expect some sort of a prediction from solving your initial value problem, if, for example, it describes, I don't know, the behavior of the bridge subject to wind, or behavior of the bridge if it's crossed by a particular type of traffic. It turns out that actually you can model these physical and engineering phenomena by using initial value problems that are significantly more complicated than what we're solving here, but nevertheless. And so if I expect my initial value problem to model a physical situation, then I would hope that typically the model or an initial value problem will produce a single solution, because if the problem has more than one solution, then what sort of prediction about the bridge I can make if I don't have a single behavior, but maybe if two different types of behavior are predicted. So typically you would want a unique solution. So then from a theoretical point of view, it would be interesting to know, just by looking at your initial value problem, whether or not it will have a unique solution, the unique solution. And apparently the answer to this question is yes, that in certain cases you will be able to make that prediction. And how would you do that? Let me write down the following here. So we want to know whether a solution of an initial value problem And let's write down the first order initial value problem. Y prime equal to f of x y, y of x0 is equal to y0. What I want to know is whether the solution of this problem exists and unique. So here is the following idea. Let me again formulate what I want to say graphically. Let's say we're looking at the xy plane. I pick a point x0, y0. Right, that's my initial point that I'm considering here. And let's suppose that around this point x0, y0, I can find a rectangle, and let's call this rectangle R, such that x0, y0 is a point inside R. So I'm going to suppose that there exists a rectangle R containing the point x0, y0, and such that the function f of xy and its partial derivative with respect to y, that they are both continuous. On R. So then, the answer to this question that I asked here, whether or not the solution of the initial value problem exists and is unique, so let's label this as IVP. Then IVP has a unique solution, the unique solution. So things seem to be, should not be clear why things would be somehow related, but nevertheless, that's a provable fact. So you have an initial value problem where you have an ODE in a normal form of the first order. If the right-hand side of this ODE near your initial point is a continuous function, and its derivative of the right-hand side with respect to y is also a continuous function near x0, y0, then the initial value problem will have a unique solution. So let's try to apply this theorem to the problems that we already looked at. So let me go back. And the first problem we looked at was, let's say this one. So the question, does this IVP that I just copied, does this guy have a unique solution? Again, unique means a single solution. and no more. So how do I answer this question? I have to apply this result that I just mentioned here. So in this case, I would write the equation in the normal form. And writing it in the normal form involves solving for y prime. So y prime in this case is minus 3x squared y squared. So therefore the right hand side f of x y is 3x squared y squared. And the partial of this with respect to y will be 6xy. Now, both of these functions are continuous, right? Because both are polynomials in terms of x and y. So both of these are continuous, in fact, everywhere. And because they're continuous everywhere, in particular, they are continuous near the point, near the initial point, 0, 1. And so we conclude that the initial value problem has the unique solution. So it then makes sense to look for this solution because you know that whatever solution you find is the only possible solution of this equation. And you should be able to find it because it is there. In fact, above we did find the solution of this initial value problem, but in this case I don't actually find it. I simply, without finding it, I'm able to demonstrate the solution, the single solution must exist. And let's do one more example with this problem. So here, remember, we had not one, but at least 4 solutions. 0, x cubed, minus x cubed, and a piecewise defined function here. Well, so let's see what we can say in this case. So another example is a solution of this IVP, or rather not is but does. It exists, and is it unique? Okay, so that in this case, my f of xy is 3xy to the power 1/3. And that certainly is a continuous function. In fact, it's a function which is continuous for all points xy. Now, then I compute the partial of f with respect to y. And that is going to be, in this case, 3 times 1/3 x y to the power 1/3 minus 1. So it's x y to the power minus 2/3. And this function is continuous as long as y is not equal to 0. Well, but, and so what that means is that, again, if I illustrate this graphically, what this means where is y equal to 0? Y is equal to 0 on x-axis. So as long as we stay away from x-axis, then the function is continuous. But our initial value problem is formulated at this point. And this point lies on x-axis. So if I draw any rectangle that contains my initial point, then df dy is discontinuous. On any rectangle containing the origin. Right? Because it always will have a discontinuity when y is equal to 0. And so from this, we conclude that we cannot guarantee existence and uniqueness at least using the theorem as or this result that I formulated it here. We cannot guarantee the existence and uniqueness of a solution. Okay, so, and that actually, because we cannot guarantee existence and uniqueness, and in fact, again, let me emphasize that in this case, what we saw was that this initial value problem actually has a lot of different solutions. So somehow this illustrates a theorem that when the conditions are not conditions of a theorem are not met, conditions that enforce existence and uniqueness, that guarantee existence and uniqueness. If those conditions are not met, then all bets are off, that your initial value problem might not have a unique solution. Okay, and the last fact that we're going to use in the next lecture that I wanted to mention here, suppose that the initial value problem y prime equal to f of x y, y of x 0 is equal to y 0, supposes this problem has a unique solution. Now, remember our interpretation of the initial value problem, of initial value problems as curves on the plane, right? So the way I interpreted the initial value problem before, I said that what the differential equation does, it tells me what the slope of a tangent line to a curve is supposed to be at any point on the plane, and the initial condition gives me an initial point. So then, let's say I have a point x0, y0. The question is it possible for me to have two different solution curves that go through the point x0, y0, like that. So maybe y1 of x and y2 of x. Can I have two functions that satisfy the ODE and they intersect at the point x0, y0? So is this possible or not? And clearly the answer is not, because if they were intersecting at the point x0, y0, then I see that both of these functions start at x0, y0, both solve the ODE. That means that both solve the initial value problem. But that is not possible because the initial value problem has a unique solution. So if y1 and y2 both satisfy the ODE, then this situation cannot happen. And so from this we conclude that if any initial value problem associated with a given ODE has a unique solution, then any two solution curves cannot intersect. So in other words, again, if for any choice of x0, y0, this initial value problem has a unique solution for a given ODE, then, as we already said, right, the ODE of the first order has a solution which is given to you by a one-parameter family of solutions. So there are infinitely many solutions of a given ODE. If each initial value problem has a unique solution, then the conclusion is that no two solution curves in this one-parameter family, once you draw their graphs, they will not intersect anywhere on the plane. And we'll use it next time to actually predict solutions of a certain type of equation that we're going to call an autonomous equation.